In 1852, a young man named Francis Guthrie was colouring a map of the counties of England. He had a rule: any two counties that shared a border had to be different colours. 2 colours, 3 colours, 4. He noticed something strange. Every map he tried, no matter how complicated, could be done with at most 4 colours. This was suspicious. The map of England, the map of France, the map of any country he could think of, 4 colours always seemed to work. Guthrie asked his brother, who happened to be a mathematician. His brother could not prove it. He asked his teacher, the famous Augustus De Morgan. De Morgan could not prove it. The question began to circulate. Mathematicians tried for 124 years to prove or disprove what came to be known as the 4-color theorem. The statement is brutally simple. Any map drawn on a flat plane, no matter how complex, can be colored with at most 4 colors, such that no two adjacent regions share the same color. When the proof finally came, in 1976, it was a proof unlike any other in the history of mathematics. It required a computer. It checked 1,482 cases by brute force. It took 1,200 hours of CPU time, and it sparked one of the most heated philosophical debates mathematicians have ever had about what a proof actually is. To understand why this is surprising, start with examples. 1 color is obviously not enough. The moment 2 regions share a border, you need at least 2 colors. 2 colors is not enough either. Imagine 3 regions, each touching the other 2, like a tri-pointed Mercedes star. Each region needs a different color from its 2 neighbors, so you need 3 colors at minimum. 3 colors is also not enough. The classic counterexample is 4 regions arranged in a wheel, where one central region is surrounded by 3 regions that each touch the center and each other. The central region needs a color different from all 3 outer regions. The 3 outer regions each need different colors from each other. That requires 4 colors. So 4 is the floor. Some maps require 4. The question is whether 4 is also the ceiling. In 1890, the British mathematician Percy Heawood proved that 5 colors are always enough. The proof of 5 colors is elegant and short. Heawood was confident the bound could be improved. For 90 years, no one could prove 4. Many tried. Some announced proofs that turned out to be wrong. The mathematician Alfred Kemper published a proof in 1879 that was widely accepted for 11 years before Heawood found a flaw. The question was, in some sense, the most famous unsolved problem in graph theory. Until it wasn't. The breakthrough was a reformulation. Instead of thinking about maps as collections of regions, think about them as graphs. Place a vertex in each region. Draw an edge between 2 vertices if their regions share a border. A map becomes a graph. Coloring regions becomes assigning labels to vertices, with the rule that adjacent vertices must have different labels. The graphs that come from planar maps have a specific property. They can be drawn on a plane without any edges crossing. They are called planar graphs. So the 4-color theorem becomes, every planar graph can be properly colored with at most 4 colors. This reformulation is critical for 2 reasons. First, it strips away geometric detail. You no longer care about the shapes of the regions or the lengths of the borders. You only care about the abstract structure of which regions are adjacent. Second, it connects the question to a rich theory. Graph theory has tools, theorems, and structural results that map theory lacked. Once stated as a question about planar graphs, the 4-color theorem becomes attackable by methods like Euler's formula, structural induction on graph minors, and the deep theory of reducible configurations, which is exactly what Appel and Haken used. In 1976, Kenneth Appel and Wolfgang Haken at the University of Illinois announced they had proved the 4-color theorem. Their strategy had been developing for years. The core idea is called the discharging method, combined with reducible configurations. A reducible configuration is a small piece of a graph with the following property. If every graph that does not contain it can be 4-colored, then every graph that does contain it can be 4-colored too. The configuration is, in this sense, removable from the question. The discharging method shows that every planar graph must contain at least one configuration from a fixed list. If that list of configurations is finite, and every configuration on the list is reducible, then by induction, every planar graph can be four-colored. Heinrich Hesch in the 1960s had pioneered this approach and shown that in principle, the four-color theorem reduced to checking that a certain finite list of configurations was all reducible. The list, Hesch estimated, would have thousands of configurations. Each configuration would need to be checked, one by one, for reducibility. This is exactly the kind of problem a human cannot do by hand, but a computer can. Appel and Haken refined Hesch's list down to 1,482 configurations. They then wrote computer programs to check each one for reducibility. The programs ran for 1,200 hours on an IBM machine at Illinois. Every configuration came back reducible. The theorem was proved. The mathematical community was deeply uncomfortable. A proof, traditionally, is a sequence of logical steps that can be checked by a human. You read the proof, you verify each step, you agree or you don't. Appel and Haken's proof was thousands of pages long and required a computer to execute. No human had ever, or could ever, manually verify the case-by-case checks of all 1,482 configurations. The proof's correctness depended on the correctness of the computer programs and the underlying hardware. Some mathematicians refused to accept the proof. They called it incomplete. They wanted a proof that a single human could read and verify in their lifetime. Others embraced the proof as a new kind of mathematics, where computer assistance was a legitimate tool. The controversy was, in many ways, philosophical. What is a proof? Is a proof an object, a thing you write down, or is a proof a social process, something that a community of mathematicians eventually agrees on? If a proof requires a machine, has the machine become part of the community? In 2005, Georges Gonthier formalized Appel and Haken's proof in the Coq proof assistant. Every step, every case check, was verified by a logic system that itself can be inspected by humans. The Coq proof is, in a strict sense, completely rigorous. The controversy did not go away. It became smaller, but the era of computer-assisted mathematics had begun, and the four-color theorem was its first major monument. The four-color theorem, as a statement about flat maps, is fully proved. But many natural generalizations remain open or fully different. On a torus, a donut-shaped surface, the analogous theorem requires 7 colors. This was proved by Herwood in 1890 and Ringel and Youngs in 1968. 7 colors are sufficient, and there exist torus maps that require all 7. On a Klein bottle, 6 colors. On other surfaces of higher genus, the Herwood number formula gives the answer. On 3-dimensional surfaces, the question changes entirely. There is no upper bound. You can construct 3-dimensional regions where any finite number of regions can be made mutually adjacent. So the 4-color question, in 3 dimensions, has no analog. The list coloring conjecture, posed by Wiesing in 1976, is a related question that remains open in important cases. List coloring is harder than ordinary coloring, and many of the structural arguments that work for the 4-color theorem fail in the list coloring setting. More broadly, the chromatic theory of graphs, how many colors are needed for various classes of graphs, is a deep, active area full of conjectures and partial results. The 4-color theorem cracked one cornerstone, but left many doors locked. A common complaint about Appel and Haken's proof is that it is, by the standards of pure mathematics, ugly. It is 1,482 case checks. There is no central insight, no elegant lemma, no moment where everything clicks. This is a real tension. Mathematicians value elegance. The best proofs feel inevitable, like the only natural path from premise to conclusion. The 4-color proof, by contrast, feels like a brute force search. There is a hope, still active among graph theorists, that someone will eventually find a short conceptual proof of the 4-color theorem. A proof that fits in 5 pages, a proof that has a single big idea. No such proof has been found in 50 years of trying. The proof, it seems, may be genuinely complex. The complexity is not a failure of human cleverness. It might be inherent to the problem. This raises a deeper question. Are some theorems intrinsically difficult to prove? Is there a sense in which the four-color theorem's natural proof is large, and any short proof is impossible? We cannot answer this. We can only observe that despite enormous incentive and enormous effort, the proof has not shrunk. The 1482 configurations remain, reduced to less than 1,000 by modern improvements, but still very many. Maybe the universe of mathematical truths includes truths that have no short proof. Maybe the four-color theorem is one of them. Today, the four-color theorem is settled. Maps can be colored with 4 colors. The proof exists. Computer-assisted proofs are now common in mathematics. The Kepler conjecture in 1998. The proof of the existence of certain finite simple groups in 2004. Formal verification of major theorems in Lean and Koch. The four-color theorem was the first. It opened the door. The Guthrie question, born in 1852, posed casually, resisted for 124 years, is now a textbook result. Every graph theory course teaches it. Every mathematician knows the statement. The proof, however, is rarely taught in detail. Students learn that the theorem is true and that the proof requires a computer. They are not asked to verify it. They are asked to trust it. This is perhaps the deepest cultural change the four-color theorem brought to mathematics. Not the result itself, which is just a fact about flat surfaces, but the realization that some truths in mathematics arrive with a permission slip from a machine. We trust the machine because we can audit it. The auditing is itself a kind of proof, and the boundary of what counts as proof has, since 1976, been slowly expanding. A young man named Francis Guthrie noticed something about a map. The notice traveled, hand to hand, through the mathematical community for a century. Then a computer in Illinois checked 1,482 cases, and the notice became a theorem. 4 colors. Always enough. No more.